And the first thing I want to do is to actually share my screen to show you something, which is what I would do in the classroom. Okay, I think now you should be seeing some weird echo effect. And if I do this, you are seeing my screen. Are you seeing my screen? It's a white screen with red writings on it. Oh, right, but I cannot read you. Coming. You're saying yes, thank you. Okay, so this is a review of things that we've seen together. So remember, we are talking about moving average processes. They are the way in which in statistics we write down the classical moving average that you hear about in finance, in technical analysis. You can see one example at the top here of this screen, which is kind of a whiteboard if you want. And we will discuss the properties of a moving average very quickly. I told you that by inspection it is a linear statistical process. Therefore, only the first two moments, including the autocovariances, will matter. Therefore, being linear, if you establish a weak stationarity, that's equivalent to strong stationarity. So we only care for moments, really. And then I kind of argued that it must be weakly stationary because it is a weighted combination of white noise processes. And you know, white noise process is the most stationary process you can think about. So if I weight and combine them, I sum them, I get something that is stationary. That is credible, but it's not a real proof. And the next thing I did is to actually show with brute force, if you want, that the process is actually weakly stationary. And if you look at your notes, I did that in three steps. The first step is to show that the unconditional mean is constant and does not depend on time. And if you look at your notes, we found that the unconditional mean is just mu. Second step, we derived an expression for the unconditional variance, which is basically just a function of the square thetas, these guys, these coefficients that you see here, all multiplied, all summed and multiplied by sigma square epsilon, which is the variance of these, that's the variance of the shock here. And finally, third step, we are talking about autocovariances. And I told you that qualitatively, the autocovariance function, and therefore the autocorrelation function of a moving average process, dies off when H is exceeding Q. Okay, now Q is the order of the process. Like in this case, in this example, Q is equal to 2. There are only two legs of epsilon on the right-hand side. H, remember, is the order of the autocovariance, which is, for instance, look at this case. This autocovariance is a gamma 2, so H is equal to 2, because I'm trying to covary the YT, so the current value of the time series, with the two legs of the time series itself. So the 2 is the number of displacement, the number of legs, which I apply after the comma when I compute my covariance. And so the point was that when H exceeds Q, so Q plus 1, Q plus 3, Q plus 4, and so forth, the gamma H corresponding, they're all equal to 0. So essentially, a moving average process has memory, as the linear memory, if you want to be precise. But this memory is limited because the memory is exhausted after Q periods. So starting at Q plus 1, the autocovariances are equal to 0. And this led to an interpretation of moving average processes in finance as processes in which financial markets, they are inefficient, but the inefficiency exhausts itself after Q periods. So there is inefficiency, meaning that news shocks, they take time to be incorporated into prices and returns. Returns is better. But after Q period, so after a while, all these news and shocks, they do get incorporated into prices and returns. Okay, so finally, at the whiteboard, I did the calculations for gamma 1 with you. I did the calculations for gamma 2 with you, I trust. And I was about to talk about gamma 3, or I just did that, okay? Now, in the case of gamma 3, we're looking at the covariance between yt and yt plus, yt minus 3. The plus 3 that I was about to say is not what is written in front of you, would not be incorrect. It is also possible to compute autocovariances between the time series and its future. It's less natural, but they are still autocovariances, and they can be used in the same way as the autocovariances you are exposed to, the one that you see in front of your eyes. You will see them appearing in the lab in eViews at one point in time. So I'm just saying that. And here, there is this small typo. Here I'm doing the calculation for you. So what is the covariance between yt and yt minus 3? Well, in place of yt, I'm writing the process followed by yt, which is copied from up here. And in case you're wondering, you may ask, where is mu? What is the constant? Well, being a constant, it cannot covary with anything, so we can drop constants when we do calculations of variances and covariances, when these are additive constants, like mu in the process. In place of yt minus 3, in place of this guy here, it's a random variable, I wrote the process for yt minus 3, which is what? Well, it's the same process followed by yt when you lag everything which appears on the right-hand side of the process 3 times. So instead of yt minus 1, this guy, I've got yt minus 4. So it's lagged 3 times. Instead of yt minus 2, instead of epsilon t minus 2, I've got epsilon t minus 5. Apologies, sometimes it will happen that I say y, and I mean epsilon. I don't know why my brain is doing that, but I try to actually control myself. And instead of epsilon t, you have epsilon t minus 3 on the right-hand side. Now, the point was that when you are about to compute this covariance, you can do the same things that we did in class. So the covariance between the sum of random variables is the sum of the covariances of all possible pairs. So it is the covariance between theta 1 epsilon t minus 1 and theta 1 epsilon t minus 4. It is the covariance plus the covariance between between theta 1 epsilon t minus 1 and theta 2 epsilon t minus 5, and so on. So there are 9 of them, because you got 3 things before the comma, 3 things after the comma, and so there are 9 possible combinations. But if you inspect those covariances, you will discover that all of them, they have the same structure. They are the covariance between some epsilon at some time and another epsilon at a previous time, when there is no possible overlap between the epsilon before the comma and the epsilon after the comma. So you will be studying the covariance between epsilon at time t minus 1 and t minus 4, between t minus 1 and t minus 5, between t and t minus 3, between t minus 2 and t minus 4, between t minus 2 and t minus 5, and so on, 9 times. In all cases, however, what you will invoke is the white noise property of epsilon t, meaning epsilon t does not remember the past and it cannot forecast the future. It carries no linear dependencies in it. And so all these covariances in pairs, which I just mentioned, the 9 covariances that you will be computing, they're all equal to 0. So if you sum zeros, you get 0, and this justifies why you get this final outcome here. And so point is that for this example, for this case, when h is in excess of 2, and 2 is equal to q, because we are looking at the moving average 2 process, what happens is that all the gammas, so gamma 3, gamma 4, gamma 5, gamma 7 billions, whatever you are computing, they will be equal to 0, i.e., the autocovariance function and the autocorrelation function, they die off, they die away when h is exceeding q. So in correspondence to 2 or 3 is a matter of taste what you write. Maybe you want to write 3 here. It's better. Now, so let me add something. I'll do that in real time as if I were writing on the whiteboard. So even more generally, and this will not be lost because it is recorded, right? Am I recording? Yes, I am. Even more generally, okay, for a moving average Q process. So I want to talk about the general case of Q. If you compute, okay, now I will put out a general case. So I want a gamma h. So compared to the whiteboard, this way of doing things, there's one advantage and one disadvantage. It's quicker, okay, but it forces me to actually copy things which are already floating on the page and then change the pedices, the indices, stuff like that. So there is a second, as it just happened, in which I copy something and that something is not what I want. And then I go in and fix it, like changing these pedix here, okay? So you have to wait like half a second, 1 second before copying whatever happens, if you're copying, because anyway, everything is recorded. Okay, so let's give a definition to this guy. So this is just the general case of this. So it's the covariance between y times t and y times t minus h. And since we are here, let's do a bit of review. That's a measure of linear dependence. Dependence means how much you remember. We also call it memory. And I think I also called it a few times structure. But it's linear memory, linear structure, linear dependence. Why linear? Because as you may remember from statistics or econometrics 1, covariances are measures, they are linear measures. So they do capture how things, random variables, move together, but only in the linear part. If there is any non-linear part, and we'll talk about that in the future, the covariance is not the right tool to do it. So it will actually possibly lie. But okay, for now, it's linear. All right. Now, I'm doing the usual. So if I have a covariance like this, what I want to do is to write inside, so in place, let's go to new line. I want to write what is yt and what is yt minus h. And instead of using the example, I want to do the general case. So what is yt? So yt is the constant, mu. And then if you look at your notes, here I have to fish some new things. You have a sum, all right? And the sum goes between j equal to 1, little j maybe, and the upper limit is given by q of the coefficients. The coefficients are called theta j, if I place them here, which multiply legs of the epsilon guy. So I call them in general epsilon t minus j. And we have to remember to also include the contemporaneous shock, which is the true shock, if you want, the shock that you expect to find in a regression, and that's called epsilon. So this is this entire expression wants to be just yt, based on our definition of what is a moving average process. Now I'm going to copy on the right of the comma, so the second y that I want to covary with, the same expression, and leg it by h periods. So mu remains the same because it's a constant. If you leg it, nothing happens to it. But instead of finding yt minus j here, I will find yt minus j minus h. And also this guy here is not it's not epsilon t, is epsilon t minus h. Okay. All right. So this is the general expression. Now, this quantity can be broken down into all the possible combinations that you have of epsilons on the right-hand side. And in each case, there are q legs, and there are many of these guys. So let me try to write that. So this becomes the sum. Sum actually goes between 1 and q plus 1 because we also have to take into account of the presence of epsilon t. Or a more elegant way to do that is actually to do the sum between 0 and q. And you need a double sum because you're summing as you run through the terms here, but for each of the terms before the comma, you have terms after the comma. So it's a double sum. In a double sum, the only thing that you have to be careful about is to change the index. So you also need this type of index. And there are things coming from here, so they have an index theta j, and you got things coming from here, and they got an index which is called I. All right. Now you need a covariance in front of it, so let's do that in steps. Sorry. There are also big square brackets that you can use in this software, so let's be pretty about it and use the big square brackets, not the small ones. But doesn't matter. Okay. Now you know that the covariance of a sum is the sum of the covariances, so this actually becomes, let me just copy it, okay, but the covariance is now they go inside. Okay. Now you can get rid of the big parentheses in front of things. You do not have to, it doesn't change anything, but right, it's not bad to do it. And the last thing I can do cheaply is to actually have the coefficients, the theta j and theta I, there is a comma missing here, come out. And so this way of writing the covariance is okay in terms of explanation, but if I leave it like that, there is a comma which I wouldn't know how to place, so let's keep it like this. So that's the right thing to say. Okay. And at this point, so I take out the coefficients, no problem with that. The coefficients can come out of the covariance, but not of the sums, because the coefficients themselves, they include j's and i's. Okay. So if they come out of the covariances, I can actually kill them inside. Okay, and finally I've got these guys. Now, the problem is h, in the sense that if I set h, so this is a general expression which always holds. But if you compute the gamma h, well, actually, let me write text at the bottom for h exceeding so that's greater than q. Equivalently, you can write that h is greater or equal to q plus 1. These are the equivalent expression because I've told you that h is just a natural number. Then all these guys, they will be equal to 0. Why? Because structurally, if h exceeds q, there will be no overlaps, which is the same phenomenon that we saw here in the case of gamma 3. Then all these guys, they will be equal to 0, because epsilon t, let me copy this guy here. To be precise, you would say that the time series of epsilon t, and I have a way to do that by fishing the right parentheses. There is a parenthesis in here, which is the appropriate one. So this is a way to denote the time series of epsilon t is white noise. Therefore, if h exceeds q, the implication, so I think there are errors which I can use to actually simplify, gamma h becomes 0 in this case. So that's the general statement of the property that anytime I specify a gamma h with h exceeding q, so from q plus 1 and onwards, all these covariances, they die, they are equal to 0, and therefore this gamma h becomes 0. Obviously, when h is less than q, some of these guys will not die, so they can be actually different from 0. And when they are, as we saw in the example, if you go above, when they are different from 0, they are simply equal to sigma square epsilon. Okay, that's what I wanted to say. That's what I would have written on the whiteboard. Let me save and go back to the slides. All right, you see the slides, right? Guys? Hello? Can you hear me? Okay. Just one. Grazie. So, okay. Now, these are the formulas that you saw in action. They're written in general form. So on the mean and the variance, I think it's fairly easy to generalize the things that you saw happening on the whiteboard last week to the formulas that you see here. Now, the formula for the autocovariances, the most important thing is not really the expression, although you saw this type of expression on the whiteboard. What is interesting is actually what you see at the bottom here. So that these gamma h's in general, they can be different from 0 when h is between 1 and q, and they die off, so they're all systematically equal to 0 when h exceeds q. Now, this is important, and you also got the picture from last week at the whiteboard, because that is the way in which you will be able to spot. You will see examples in a moment moving average processes in the data from far away. You will look at the ACF and you will see that suddenly the ACF drops to 0, or in the data it will drop to non-statistical significance, and that will be an indication that you're looking at a moving average process. Now, this expression, do not memorize it. I don't want you to memorize things like this. It's a bit special because there is a singleton. So there is 1 sigma square epsilon, this guy, which is just multiplied by 1 coefficient, by 1 theta. This theta, which is alone, happens to carry an index h, which is the same as the index of the gamma. So it refers to the last leg, if you want, of the gamma h that you're computing. And all the other terms, they are multiplying sigma square epsilon, because that's at the end of the parentheses, and they appear in pair, so they are multiplied, the thetas are multiplied with each other, and they have a fixed structure, because you see theta h plus 1 times theta 1, theta h plus 2 times theta 2, theta h plus 3 times theta 3, and so forth, up to this point in which you have the last term. But after q, as we know, they have to die off, because there is no possibility to find overlaps which generate a variance instead of generating a 0. Okay, examples. So we'll do examples on paper because they are in the slides, and so they come from the book, and so you have to see them, look at them. And then I will open the famous Excel file that I mentioned already a few times, which is posted, and I will show you how to play with simulated data from a moving average process. So today is quite interactive from this point of view, and to do it in the distance is actually okay. All right, first, the sentence that you have at the top of the slide is something that appeared already on the whiteboard, so I will not repeat it. So what happens is that I generated from a selected stochastic process, which I am in control of, 1,000 observations for each choice of the process. And in the slides, you see on the left the picture of the process which is simulated. So it's just one Monte Carlo, it's one realization of such process among infinite many that I could have derived. And on the right, I computed in Excel using the file that you will see in half an hour, in 20 minutes, I computed the ACF. And the ACF comes in the usual way. So you got the legs h on the horizontal axis. They go between 1 and 24. As you know, there is nothing magic about 24 in the sense that you could compute more or less. Here you can go up to h equal to 999 because I've got 1,000 generated observations. It's a bit silly to compute 999 of them, but in principle, technically you can. On the vertical axis, you got the ACF, and the scale, in principle, goes between -1 and +1, as you saw many times. But for visibility, as you see, I'm playing a bit with the scale, because otherwise we would see very little. And the dashed lines, they refer to the 95% confidence interval, asymptotic. So when you can use the critical values, ±1.96, coming from the normal distribution that we have encountered already. Okay. All right, so the first process is a very simple moving average 1, so Q is equal to 1, and the coefficient, the only coefficient, theta 1, is set to be equal to 0.3. So it's kind of small, okay? So it's a weakly stationary process by construction in which there is memory, linear memory, not much memory, if you so want. In case you're wondering, what is mu? Where is mu? Well, mu is set to be equal to 0, and therefore it becomes invisible. I mean, any number, any constant equal to 0, as you know, you can spare the effort of reporting it. Okay. Now, let's, last thing I need to tell you, on the case of epsilon, epsilon is white noise, but actually to overkill, it's generated as IID normal with mean 0 and variance 0.04. So why 0.04? Where does it come from? No, I mean, for visibility, because he gave me pictures which were nice to show, but you can play with that, and nothing really special happens. For those of you who are wondering about it, notice that in the case of a normal time series, a Gaussian time series like this one, to claim IID-ness or to claim white noise, they're actually equivalent matters. Okay, so it's also white noise, obviously. Now let me zoom inside to see things better. All right, so that, I think that's big enough, actually. We can go a bit bigger even. All right, so what can you say about this time series? So you see 1000 values, they are generated randomly when the shock epsilon are from the stated distribution. What can you see? Well, you see a series that crosses the zero, the axis, if you want, very frequently. So, and quite randomly, so very randomly, with little structure. And the zero in this case is not just the axis, it represents the unconditional mean of the series. So this is a series that goes back to zero, so the unconditional mean, quite often, very often. And honestly, I know that you see the process, and I just told you how these data were generated. Many people would not be able to distinguish this type of plot from the plot of a white noise. Now, what is the big difference? Well, this plot is of a series carrying some memory, limited, but there is some memory. There is some structure, linear structure. A white noise, as you know, has no memory whatsoever. However, the little memory characterized in this picture, to me at least, cannot be seen by naked eye. So just by looking at the picture. Now, I know that if you zoom in, you can see some cases like, can you see my little hand? I think so now. There are some cases in which for 20, 30 observations, the process seems to be able to stay away from the mean. So it's like the Roomba cleaner of your room, the little robot cleaning the floor, that actually doesn't go back to the docking station for a long time. So it seems to know where it is, essentially. It happens here in the positive. It kind of happens here in the positive again, but it happens here in the negative. But these occurrences, as we noticed, they may also happen by luck, good luck, bad luck, I don't know, in the case of a white noise. So bottom line, is very difficult if you're given this picture, just this picture, to actually tell apart the white noise from this type of moving average with very weak memory. Okay, so how do you tell them apart, right? Because in real life, we will need to know this, because, for instance, if you're facing these type of series, there may be exploitable trading strategies. There will be weak trading strategies, but maybe there is some money to be made. Answer: you have to compute and think about the structure of the ACF. And so this is the ACF coming from the 1000 observations. And as you can see, out of 24 bins, 24 little rectangles, which are marking the values taken by rho h. This is rho h, by the way, not gamma h. So it is gamma h divided by gamma 0. So it's a scale version of gamma h, but okay. So out of 24, there is only one of them which is statistically significant. It is this guy here. It is equal to 0.27 or something like that, if I remember well. It is obviously sticking out of the 95% confidence interval, so it is significant. And all the others, they are not there. And that's the typical behavior respect of the ACF, the sample ACF of a moving average one process. So gamma 1 will be non-zero, and actually the sign of gamma 1 will reflect the sign of theta 1 if you look at the expression. And indeed, that's the case, because 0.3 is positive, and gamma 1, and therefore rho 1 is positive. And all the others, they die off. So gamma 2 is 0, gamma 3 is 0, gamma 24 is 0. If I had computed it, I would hope that gamma 999 would be also 0. So when you see an ACF behaving in this way, probably you're facing a moving average one. Another thing to notice, I will be more specific later about it, is that there is no numerical correspondence between the theta 1 coefficient, which I set to 0.3, and the rho 1 coefficient that gets plotted here. So this difference is actually a structural difference. It's not just that we got a bad estimate from the 1000 observations in our case. In the case of moving average processes, rho 1, rho h is not supposed to be the same as the coefficients theta h, theta j that appear in the process. So be mindful of that. We'll see that again later. Okay, next case, that's at the top of this slide. Let me move out a second. So I'm simulating, in this case, the data from another moving average one, but now theta 1, the only coefficient we have, is equal to 0.8. So bigger coefficient, more memory if you want. And the constant mu is set to be equal to 0 again, and the shocks, the epsilons, are the same as before. So they are generated from the same distribution, but I think I also got them, the same shocks. I mean, I'm using the same numbers, which you can. I mean, there is no restriction in doing that. So the only thing that is changed between the previous slide and this slide is the body of the process, so how much memory there is. And the picture that you get is the one that you see here on the left. So you see 1,000 observations again. And okay, here you have to be a bit honest in the sense that some of you will see differences compared to the previous picture. So some of you, by looking at that, they will say, well, I see a bit of more structure here. In the sense that if you go in and you look carefully, you will see that there are many more occurrences for longer periods in which the series seems to have a power to drift away from 0, so to stay away from the unconditional mean. For instance, this happens here, see here, these are like 40 observations, so quite a long time. Let me look the opposite case. The best one, so this is another case of positive deviation above 0. It happens here in the sense that the series for 20 or so observations is able to stay below 0, to stay negative. So all in all, but it's very difficult to do because it is a visual analysis. By changing the coefficient of the series, which seems to be spikier on the one hand, and it seems to cross the unconditional mean, the 0, a bit less frequently than before. But it's a qualitative matter. And if I had shown you this, just this, not the previous plot to compare it with, many of you will be like, well, this is probably white noise. It's not, but it looks like, okay? So how do you do? So how do you tell apart this process from a white noise? Again, you have to compute the autocorrelation function for the 1,000 observations, which is the one that you see here. And it behaves the way you are expected the ACF of a moving average 1 to behave, meaning the first autocorrelation, rho 1, to be precise, rho hat 1, because it's based on data, is big, statistically significant, it sticks out from the confidence interval. Notice that it does not take a value of 0.8. That is what I was already saying before. We are not expecting the rho 1 to be equal to theta 1. If you look at the formulas, if you ask me, I can do that for you, but if you look at the formulas, it's obvious why. In the book, we speak about it. And all the other values of the ACF, they are small, close to 0, not statistically significant, and they have no structure, in the sense that here, some of them are positive, some of them are negative, but they randomly go up and down without any structure. A few of them are almost exactly equal to 0. They become invisible, but they do not tattoo. But the point, the idea is that they fall inside the 95% confidence interval. Once more, that's the ACF you expect to see from a moving average 1, meaning rho 1, gamma 1, and therefore rho 1, they will be different from 0, and they will reflect the sign of theta 1. And all the others, they will be zeros, or at least in the data, they will be not statistically significant. So, okay, score. One more case. I had to change slide. Okay. At the bottom of the slide, I simulated values from a moving average 2 process. So the one for which we did the calculations, if you want. And let me zoom in so that you just see what I want you to focus on, so the bottom. So there is now 2 coefficients, theta 1 and theta 2. Theta 1 has been kept at 0.8, theta 2 is equal to 0.3. But, I mean, in a moment you will be able to play with the coefficients and see what happens. And if you look at the plot, well, now it's becoming a bit visible, maybe, if you so want. Meaning this series is acquiring additional power, capability to stay away from 0, from the unconditional mean, for a long time, and this happens quite frequently. Now they're quite visible, I think. So it happens here, say, so there is departure from 0 for a while, for 20, 30 observations. It happens here, it happens here. Here it's glamorous. It happens for like 40, 50 observations. It happens here for another 40, 50 observations. So it happens more frequently than before. And when it happens, it tends to last more. Why? There is more memory. And why do I say so? Because now Q is equal to 2, and the coefficients, I mean, they're bigger if you sum them in absolute value than they were before. Now, if these were, they are not because I generated them, but if these were actual returns, you could say that the very first market we saw was almost efficient. The second market on top of this slide is a bit less efficient. There are bigger possibilities, opportunities to trade. This market starts being quite inefficient. So the same shot, they take a long time to be incorporated. And for instance, if you see prices down here or returns down here, so they're being negative, so this offers you an opportunity to buy because you know the things have to go back to the positive and go across zero in the following period. So the trading strategies are quite natural to use. But many people, if I just give you this picture, they will probably detect some memory. They will say, this is not a white noise. There is something going on here, but it's not difficult. Sorry, it's not easy to actually shoot just by looking at the picture what kind of memory is that. Is that AR model, autoregressive? Is that ARMA? Is that moving average? Is that nonlinear? Because just by looking at the data, just by looking at this picture, you can. It's not easy to see whether something is linear, non-linear, right? So there may be so many things that go on behind this. The only thing that is visible is that there is stationarity, in the sense that the series tends to go back across zero very often. So it tends to be attracted towards the unconditional mean, towards zero. That is visible. But you don't know whether it's white noise, it's AR, it's MA, it's something else. How do you do that? So that's the message of today, as you are actually probably understanding. The point is we need to look at the ACFs. So we need to build them, we need to use software that is offering ACFs, and we need to pay attention to them. Okay, that's the ACF for the 1,000 observations on the left. It's a moving average too, and the ACF kind of behaves in the way expected, in the sense that if you ignore something which happens down here, late in the ACF function, what you see is that there are two legs, two values of rho h, for which there is a big estimate, and these estimates are statistically significant because they stick out of the 95% confidence interval. And it's rho 1 and rho 2 as you would expect. Then the ACF seems to die off in the sense that these are small numbers, and anyway, they're not statistically different from zero. The only issue you have happens in correspondence to h equal to 21, in which you got a bin which is slightly significant, meaning it sticks out of the 95% confidence interval, as you can see, but just barely. Now, when you will face such type of situations, you have three possibilities. First, if you can, and in our case, we would be able to, because we are simulating the data, you simulate the data again. And if these rho 21 hat is just a fluke, is just bad luck, it will go away. Maybe some other fluke will appear, but not in correspondence to h equal to 21. And later, in a moment, using Excel, we will be able to do so. Second option, well, you look at the picture and you say, well, okay, I mean, there is a clear structure. The first two are significant, the others are not. And these may have happened, probably it has happened because of bad luck. And so you ignore it. And if you do, this becomes the typical ACF of the moving average 2 process, as expected, as it should be. The third option, which is a bit awkward, but we'll talk about that again in the future, so we cannot dismiss it entirely. It is useful to think about it, is to consider this a moving average 21. So there are 21 legs to the right-hand side of YT. So there are 21 shocks that are remembered. The only thing that is happening in this data is that the first two are remembered in a clear way, and also the 21st is remembered in some clear way. And what is in between, so between 3 and 20, it's not remembered for some reason. It may be that the corresponding coefficients, theta 3, theta 4, theta 5, blah, 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 theta 20, all these coefficients, they are equal to 0. But this would be a moving average 21 type of model. Now, I know that some of you are like, well, weird, strange, I know, okay? But we'll talk about that in the future. But today, based on what we see, we cannot dismiss this option. Now, Before moving away, I want to open with you for 10 minutes or so and play a bit with the Excel file from which these plots come from. So to do that, I need to share my screen again. Okay. All right. Now there is the weird echo effect. Okay. And then I will go and get ARMA simulations. This Excel file has been posted for a while in Blackboard. So if you didn't, you can go and download it and play with me now. Okay. Otherwise, you will have to endure the next 10 minutes or so, which is an explanation for where the pictures that you see in the slides and in the book come from. Okay. And it's optional. Okay. So in the exam, it's not that I will ask you questions about the Excel file or the way it was built. That's not the point. Now, this Excel file has three worksheets at the bottom, one for autoregressive processes, in which I allow you to simulate data and estimate ACFs, as you can see, for 1 and 2 legs of an AR model. And this will be very useful because I will reopen this when I have to introduce the topic of random walks, but it will happen later. There is a tab for ARMA models. This one is a limited tab because I'm just allowing you to have ARMA 1.1, which is a special case, but we'll see what it is tomorrow. And the tab we care for is the moving average process, in which I'm allowing you to actually have 1 or 2 legs. Okay. So let me actually also, okay, bird's eye view. There are 3 pictures here. So one is a picture in which the process is plotted, and I just plot 1,000 observations, as you saw me doing in the slides and in the book. Why just 1,000? Because I want the plot to be visible, meaning I wanted to be able to blow it up, to increase the size, and to actually see when there are departures above and below 0. And the 1,000 seems to be the optimum for that. Now, the truth is that the rest that you see on the page, especially the autocorrelation function, it is actually computed on the basis not of 1,000 data points, but 2,000. And this is visible if you scroll down at the end of the spreadsheet. Technically, I'm using 2012. It's not important to explain why the 12, but they are roughly 2,000 observations, all right? And why 2,000 and not 1,000? Because it offers some better degree of accuracy in the results you get from the autocorrelation function. That's all. And in fact, you will see in a moment, we'll play with that even using more than 2,000 could be a good idea. Okay, so I leave it up to you to choose whether you want to play with the Excel file and increase the number and get increasingly accurate autocorrelation functions. All right, what are all these numbers? So this is the place in which you control, in orange here, the nature of the process. You set mu, you set θ1, θ2, and you set sigma. And if I leave the process the way it is now, so everything is set to 0, so there is nothing on the right-hand side of the moving average, you're looking at the moving average 0. So here, I will not do that all the time, but that's what you should write. Now, you know that the moving average 0 process is a special case. It represents a white noise process. In a white noise process, it has no memory, it has no structure. And bird's eye view, then I will come back to this. The ACF, which I derive, I will explain in a moment how you derive it, works. So how do you read this ACF? So first of all, it's an ACF which is drawn vertically, not horizontally, which is suboptimal in my view, is a bit less natural. Why do I do that? Because I want to get used to the way in which eViews will be plotting the ACFs. So I'm doing in Excel things that will happen in eViews. So, but there is a bit of loss of clarity, I understand that. Now, inside the ACF, there are 3 things happening. There are bins in blue. These are the values of the ACF, so of rho hat h. And all the bins, in this case, they're actually small. Some are positive, some are negative, but the numbers are pretty small. If you go on top of them, it will show you the number. So we're talking about things such as 0.06, 0.07, minus 0.03, so very small numbers. And why so? Well, because it's the autocorrelation function of the white noise. The white noise has no structure, no memory, and so we are expecting the ACF to be flat at 0 or to be very close to 0. What are the red bars? So the red segments. So the one preceding a blue bin is the lower bound of a 95% asymptotic confidence interval, and the one following it, so say this one and then this one, the one following it is the upper bound of a 95% asymptotic confidence interval. When the two segments in red, let me actually magnify so that you can see better. When the segments in red, which precede and follow a given blue bar, they stick out in opposite direction, so one goes in the negative and the other in the positive, then you know that the bar, the blue bar that you are marking, is actually not statistically significant. So this is equivalent to the rho hat H falling inside the two, dashed lines in the plots that we saw before. Drawing dashed lines was not so easy in Excel, so I adopted this way of communicating it, but it's taken from software. There is SAS, I think, there is software in which the way things are presented, it's this one, so I wanted to get used to it as well. Now, if you look around, there is also numbers below, but all the red bars, they have this feature. One is sticking to the left and the other is sticking to the right. So all the little blue bins that you see in this picture, they are structurally non-statistically significant. And that's what you expect, once more, of a white noise, because the white noise process is super stationary. It has no memory of whatever kind. All right. Now, let me play a bit with it. So let's set mu to equal to 0.5. If I do that, essentially the picture doesn't really change. And the only thing that is changing in the picture is that everything is shifted up by 0.5. And that's exactly what is the meaning of setting a constant. So that's a white noise to which you are adding systematically 0.5 to all the simulated observations. Thank you. But the ACF has the same structure as before. So apart from some cases, let me actually teach you also something immediately. Now, as you know, in Excel, there is a function such that if you do not deactivate that function, every time you punch enter, all the numbers in the file will be recalculated. In these cases, there is a strong component, which happens in column B, of generating normal random variables. So if I go anywhere and I hit a key, say X, but any key is fine, and I push enter, see all the numbers are computed afresh. So adding mu is just shifting things up and down. So let's make it minus 0.5 now, minus 0.5. So everything has been shifted down. But the ACF does not lose the properties that we talked about before, in the sense that all or most of the double red bars, they stick out in opposite direction. There is only one exception which happens here in this case. But if you hit X again, probably it will go away. So let's see. Yes, it kind of did. Yes, that one went away. There is another one sticking out, but we'll talk about that in a moment. So it's not the right time. So now, as in the pictures in the slides, I will set a mu back to 0. And the point is that adding a constant or subtracting a constant does not change the fabric of a time series. It does not change the variance, as you know, and it does not change the autocovariance structure, which is the same property which I invoked when I was doing algebra on the whiteboard. All right. Now, the real game happens here, and possibly also here, but especially here, the coefficients. So let me start with the moving average one process, and let me pick the one that we had as a first example in the slides. So I'm setting θ1 equal to 0.3. So I don't know, some of you maybe saw a change happening in the sense that the process started sticking out a bit more compared to the white noise case. So if I set this to 0, you get this. See, it's kind of shrinking towards 0, towards the middle, and this shrinking derives from the fact that the process has no ability to drift away from 0. It cannot really stop crossing 0 all the time. When you start setting something like 0.3 here, see, something is happening. It becomes a bit spikier. Now, are we supposed to recognize a spike if I just give you the picture that you're seeing now? No, it's very difficult. So from far away, this still looks like a moving average, a white noise process. But when you change a white noise into a moving average process, the change, as you saw, becomes a bit visible. And the process now is doing two things which are visually clear. But to make them even more clear, let's make these into 0.8. Okay. So first, because there is some memory, the process is taking some walks. They're called walks. So there are sequences of data between 1 and 2000 and 1000, apologies, in which you drift away from 0, as we saw before. And some of them, they are quite visible. Look at this one, for instance. For 25, 30 observations, the process is structurally positive. Here, 25, 30 observations structurally negative. Here it happens again. There are many such instances. Before, if you go back to white noise, it was happening more rarely. Okay, it was still happening, but it was a matter of luck. To be precise, it was just happening 5% of the time. Now it's happening more than 5% of the time. Second, some will have noticed, some other people do not. In portions of the plots, it is as if it's very visible here in the first 100 observations. It is as if I'm using a boldface font, like a bigger font. So I'm not drawing always this line with the same size of the line. And it's just a visual impression. If you go back to the option in Excel, you will see that the line is always drawn with the same size. So what is happening? Well, it becomes like a pasty drawing. And the pasty drawing is due to the fact that there is a lot of oscillation of the time series on the place, so close to a previous value. But that's exactly what you expect. If you look at moving average one process, it means that YT depends on epsilon t minus 1. So the last shock, which is a relative of the last value, is actually still affecting the value of the series. So these moving close to the initial value, moving in the place, say, is expecting of moving average processes, and it gives some visual effects. Still, some people will not be able to detect the nature of the process just by looking at the picture. Now, let me comment on the columns B, C, and D. What's happening here? So column B is the moving average, is the process that which I am simulating, and it seems to be the sum between C and D. So what is happening in C, what is happening in D? So D contains the random shock. So in the slides, it was normal, mean 0, and variance 0.04. In this case, it is normal, mean 0, and the variance is the square of 0.1, which is 0.01. So there is a slightly smaller variance in these simulations compared to the slides. And the way you get the numbers is the one that you see here. Okay, it's very simple. So you just draw a uniform, you go through an inverse CDF transformation, and you multiply by sigma. That's the way you generate normal random variables in Excel. It doesn't matter to us in the sense that I'm not requiring you to know this, but just to comment. Okay, once I have the shock, in column C, I'm setting up the conditional mean. The conditional mean is what? Is the body of the moving average process when you drop epsilon t. Why? Because epsilon t is given in column D. And so everything else, which is not the epsilon t shock, the current shock, is inside column C. And in column C, you see what? Well, you see the constant mu, which lives in cell C4, plus the coefficient θ1 that multiplies the most recent shock in column D, plus θ2, which lives in C6, which multiplies the shock generated in column D 2 periods before. Why so? Because in principle, this is to be a moving average 2 process. Then I sum, say, row by row, cell by cell, and you get the values which are plotted in the picture. Okay, so what is the ACF function? The ACF function is computed here at the bottom. So the values of the ACF are computed here using, this speaks Italian, but in English, the function is Correl. Okay? And it's just a simple function in Excel, and Excel does not actually force you to copy and paste nearby series. You can do that in that way. It's clear because you have a visual of what you're doing. But if you want to compute autocorrelation, it is enough to use the correl function when you are essentially lagging the values that you put before the comma, actually the semicolon in this case, and after the comma. So you just have to slide the values at which you start and the values at which you end your time series, your 2000 values, to be able to do the calculation. So you do not even have to do copy and pasting. Okay? So the ACF values are computed here, and they go between h equal to 1 and 24. So in the first one, you see that you are correlating observations B14 and B13, so there is one leg of difference between them. If you scroll down to h equal to 24, you are correlating B37 with B13, B13, and the legs between them is equal to 24 observations as desired. Now, around the ACF values, then you build the lower and upper bound of your 95% confidence band. And so these values are built around the center, which is given by the estimate of rho h. So you see I4. And for the lower band, you deduct 1.96 divided by the square root of the number of data points that you have, square root of t, we said in class. And on the right, you take the rho hat h and you add 1.96 divided by the square root of t. So these are asymptotic confidence intervals because, as you know, they hold only if the sample size grows towards infinity. In my case, I've got 2000. 2000 is not a small number, but there are issues about the reliability of these confidence intervals. But if you take the Excel file, you extend it to 20,000 observations, 200,000, maybe you can do 2 million, I'm not sure, but 200,000 for sure you can do it, then these will become increasingly accurate, and they will represent the truth. Sorry. Okay, finally, let's look at the ACF. And as expected, it shows the behavior that that you should have, in the sense that there is one bin sticking out. It's really big, and it does not correspond, however, to the value of theta 1. Theta 1 is equal to 0.8, and you get something like it's written here actually, you get 0.5, 0.49. Sorry. It is highly statistically significant, as you can see, because both the red lines, they stick out to the right in the same direction, but there is some sample uncertainty. And actually, in this case, we got particularly unlucky because we have a bunch of them. They are these guys. They are actually 5 in a row, which are also statistically significant. See, the ACFs, they're not very big, but both the lower band and the upper band, they stick out to the right. Now, that's a particularly bad realization of the ACF of moving average one process. Actually, yesterday I played around with your colleagues of class 15, and nothing so bad happened. And so if you are like discouraged, oh no, don't be. You hit X again, you change the data. See, these data, they seem to actually jiggle a bit more than before, and the ACF now looks much better, in the sense that there is the first bin, which is highly statistically significant, as expected, again, is equal to 0.49, a value very similar to before. And most of the other things I see, let's see here, now they go well. There is one guy here misbehaving slightly, because this looks statistically significantly negative, and there are 2 guys here that give some problems, but okay. Now, so let's focus on the guys that give problems. These are legs 18 and 19. So let's hit X again. The general shape of the ACF stays the same, but let's look at 18 and 19. Now one of them no longer gives problems, and 18 stays, but there is also an issue with 16 and 17. Let's hit X again. And all right, so that's quite different now, I have to say. Now let's look at this one. There are no problems anywhere, I think. All right. Oh, yeah, there is a little problem here. So almost the perfect ACF, apart from row 2, in which this guy is sticking out slightly from the confidence band. Now, what is happening? Well, it's very difficult. So if you play a bit, you will get it. But it's very difficult to get the perfect ACF that we are expecting. Why? Because we are using only 2000 observations. The perfect ACF will come out if you simulate a sufficient number of observations from the process, and 2000 seems to be okay in terms of describing the general shape, but not quite okay in terms of keeping all the little bins that you have here not statistically significant. Okay, and either you play and you average a large number of simulations, or you build longer simulations to have the ACF behaving in the perfect way. Another thing, but maybe I'm repeating myself in this case I apologize. Notice that the ACF in corresponds to the first log is not equal to 0.8. We simulated from 0.8, but we do not get 0.8. Now let me quickly play. So first of all, let's do something like this. So θ1 can be negative. It can. There is no problem with θ1 being negative. You get something that, again, from far away, I don't know if you would be able to disentangle and distinguish from a white noise process. And the ACF, however, has a similar structure as before. The only difference is that the first bin sticks out in the negatives, because the row 1 hat now is a negative autocorrelation, not equal to the coefficient we have generated the data from. Actually, if I see carefully, in this case, there are little problems. There is just a bit problem with the third autocorrelation, but everything else is fine. Let's do one more. So also, we'll talk about it, but in principle, there is no problem with coefficients being large. So let me put a 3 here. And I don't think this plot is qualitatively different from plots that we saw before. And see, the ACF is not equal to 3. It's not equal to a crazy number. It's equal to 0.3. Actually got smaller than ACFs that we saw before. And actually, the resulting ACF is quite well behaved in terms of significance and stuff like that. Okay, finally, let me close by doing the same example that you saw in the slide, so 0.8 and 0.3. Now, let me do a transition like the following. Let me put 0.3 here, and set this equal to 0. So that's a starting point. So this is a process with some memory. Some of us will not be able to distinguish that from a white noise. All right. Now I set this guy to 0.8, this guy to 0.3. And I think that the time series that you got now is a bit different in terms of qualitative patterns compared to the one that you saw before. But again, it's very easy to detect the difference. That's a moving average 2 now. It's very easy to detect the difference when you leave one process and you go into another one, because you have the visual changing in front of your eyes. But if I just give you this and I ask you, look, is this a white noise or not? It's okay. Some people say, look, I don't know. I mean, it may be a white noise, and just an unlucky white noise, but it is a white noise. But if you look at that, there is visible structure now. So there are very long walks taken all the time. So most of the observations, they come from walks. Actually, now it is possible to do an opposite process. So you can single out in which parts of the process it still tends to behave like a white noise. It happens here around observation 200. It happens here around observation 700, more or less. It happens here around observation 500. But for the rest, it doesn't look very much like a white noise to me anymore. But still, it's hard. So how do you detect what's going on? You have to look at the autocorrelation function and either have lots of simulations or repeat many alternative simulations. Now, on the positive, we have what we expect. The first two bins, they stick out. They're highly statistically significant. They're not equal to θ1 and θ2. They are equal to 0.6 and 0.16, whatever they are. But there may be some problems, some issues down the road. So some values of the ACF, which they give some evidence of being statistically significant, even if they are not, and they cannot be. So like here, it happens at 21, 22, and 23. But these will not be robust to repeating simulations. So if you have X again, you get something else. And now, as you can see, 21, 22, and 23, they no longer give problems. Actually, there are some problems with row hat 3 at most here. But see, the location of the random statistically significant ACF values keeps moving as you repeat the simulation, which is an indication that the only robust findings is this, the first two bins. They are statistically significant. Okay, in case you're wondering, but I will not exploit that very much. But on the right, I'm also plotting moving averages. So these are different moving averages over 10 periods, 20, 50, and 252 periods, thinking about 1 year, derived from the data that were simulated to the left of the spreadsheet. And why do I do that? The idea is that the more memory there is in a time series, the less frequent, but the more visible the crossings of different moving averages of different lengths will be. And I'm doing this because ARMA models, as I already told you in the classroom, they are closely related to technical analysis. So there are people who actually use these models as a surrogate to comparing moving averages. And there are people that systematically and professionally do compute and compare moving averages. And what they do is something like what you see in the picture. They derive trading signals from situations in which the long run moving averages, they go above or below the short run moving averages or vice versa, as you want. And the idea is that the more structure, the more memory there is in a time series, the less frequent the crossings between different moving averages will be, but the more meaningful these crossings will be considered by the analyst. Like if you are a technical analyst, when something like, I don't know, like this happens, so the short run, I don't know if you can see my little hand here, probably you can now. When the short run moving averages, so the 10 period, 20 period, and 50 period, they all cross and go above the long run moving average, this will be a trading signal. I think, I mean, simplifying, that what they will say is that the market is in overbought, so there is too much buying pressure, and this could give a signal to actually sell a bit of your holdings of this asset, of this stock, say. And when the opposite happens, look at this case here, for instance, this will give a signal. The signal lasts actually something like 30 periods, could be like a month, that you probably have to buy because all the short-run moving averages are below the long-run moving averages. Now, you are still trying to find a way to capture the presence of memory. My claim is that the best way to capture such a presence and to think about it is the autocorrelation function, not comparing moving averages, but they give equivalent results. And in finance, we are much more used to see these than that. But here I can test for significance. I can think about shapes and patterns. There, on the right, it's much harder to do. But I will show you a few more moving averages in the future when we deal with the other types of processes. Okay, so I leave you here. I already spent half an hour, I think. Play with it if you care for the stuff. And if you find something interesting popping out, let me know. Now, I repeat, however, 2000 is not enough to have everything going for you. So pictures looking like textbook pictures. You need more, or you need to run the same simulation many times and average across simulations, which you will have to do on the side on your own, okay? 2000 is okay, but not sufficient. Okay, now you're seeing back the slides, I think. No, you're seeing nothing. Now you see the slides. Guys, can you see slides? Can you hear me? Is everything all right? Okay. If you have, grazie, thank you. If you have questions, guys, please write them, and I will stop at the right moment and read them and answer. Otherwise, we do that at the end. Okay, so we start autoregressive processes. Now, moving averages, they are important because they are the simplest kind of process with memory, weakly stationary, that you can find. They're kind of the fabric of some of the things that we'll see together. So it's important to start from them. But if you're looking for a type of process which has widespread usage in statistics and in finance, these are the autoregressive processes. Now, from far away, look at them. They look the same story. Look at the bottom, say down here. Same story. But what you remember on the right-hand side is not now the past shocks. What is remembered, is the past values of the series. Now in finance, we are lucky because we have a clear understanding for the difference between values and shocks. The shocks are the portions of values, of prices, of returns, of the things we see that we did not expect. And in finance, we actually trade shocks. We don't trade values, because values, the portion of the value which was expected, is already in the price. So it's impossible to profit from values per se. It's something of accountants to look at values. In finance, we want to know what portion of the value that we see in the market is unexpected, and we call it news, shocks, innovation. And this is what we care for. So the moving average process is a useful process. You will see that also pedagogically, because it relates prices, returns to shocks only. The autoregressive process is kind of a raw, say, case, because it relates the values of prices and returns to past values of prices and returns, not only to shocks. So that's the big difference. However, if you look at the empirical practice of statistics and econometrics, for a variety of reasons, some of them understandable reasons, some of them, I don't know, less understandable, say, there is much more emphasis in using autoregressive processes compared to moving average processes. So what are the confessable reasons? Well, there is one. After all, an autoregressive process is a regression, and it can be estimated, more or less, using the methods for regression. So I'm really talking about OLS. In the case of moving averages, there are bad news. These are not regressions, as already claimed in the classroom when I introduced them, and as such, they cannot be estimated by OLS. So if you try to use the methods that you learned in Econometrics 1, they work here on this slide, but they were not working in the moving average processes that we just saw up to this point. So historically, it's understandable. There were no computers, or very lousy and expensive computers. Historically, people for 20, 30 years stressed a lot the ability to just study regressions and apply regressions everywhere. And so when they got to ARMA analysis, this type of analysis is also called Box-Jenkins analysis, they wanted to keep doing what they learned how to do with regressions, and this was the model that allowed them to do so. And so there was an overemphasis on autoregressive processes compared to moving average processes. Nowadays, there's no longer any reason to behave in that way, but you know, AR processes, they're still very important, and everybody speaks about them. Okay, so the AR is the linear case. Better, it can be under some conditions the linear case for a general family of processes which are called the Markov processes, which I think you have encountered already in derivatives 1. Maybe they were defined in derivatives 1 as well. And a Markov process is a stochastic process, a time series process, in which the process remembers a finite number of values from the past. And sometimes autoregressive processes, they are said to have a finite memory. So there is this word memory that I've used a lot. And we'll see whether it is true or not that the memory is finite or not. So in what sense is memory finite? And the distinction will be, but you will see that tomorrow, the distinction is between remembering the level and remembering shocks. And I already told you that autoregressive processes, they are forcing you to remember everything and not just to remember the shocks. Okay. All right, so in terms of the statistics, the mathematics of the process, you see them here in the slide, but they look like moving average once you replace epsilon t minus j with yt minus j. So you're remembering everything, not just the shocks, as I said. The order of an autoregressive process is called P by convention and not Q, but they're just letters, right? So in reality, you will have numbers in place of P or Q. And but let's stick to it. So when you see P from far away, you will think about autoregressive. When you see Q, you will think about moving average. Okay. The shocks, the epsilon t, there is only one now apparently. I will explain the apparently in the future. The epsilon t that you see again is white noise, but in some occasions you may want to actually go brute force and assume that epsilon t is IID, maybe IID Gaussian, but IID, so independent over time, which is a bit stronger than just white noise. Okay, that's it. All right. Now, the last thing I do today, before actually plunging back to autoregressive process, is to define two operators quickly. They're very simple, but they will allow us to jump from logical statements about autoregressive processes to mathematical operations. Now, in this course, it has always been like that, but even more in COVID times, it is about understanding what the machines do for us. It's not about doing things. I mean, at the time of doing time series analysis with paper and pencil is anyway gone since 20 or 30 years ago, since I was a student already myself, I have to say, okay? But nowadays, I mean, it's all about understanding what computers do in the background. And so that's the spirit with which you have to study these two guys here. But sometimes, occasionally, softwares, they spit out messages or they show output. You will see that in our labs. That is mindful of the existence of these operators. And if you never encounter them, if you have no clue for what they are, then interpreting the output and reporting it becomes difficult. So you have to make up things or find out about the operators in real time, which is not optimal. Okay, the operators are two and they are related, the leg operator and the difference operator. What is an operator mathematically is like a function in your favorite software. So when you invoke a function in your software and you apply to some variable, to some set of numbers, some set of data, the variable, they get transformed into something of interest. So there is a goal and you're using the function to pursue a goal. Here is the same, okay? Now the leg operator is pursuing the goal of applying delays to the time index of a variable. In this case, it will be a random variable, but to any variable. So very simply, if I take yt, whatever it is, and I apply L, little hand, and I apply L to yt, what I get out of it is yt minus 1. Okay. Now, the leg operator has a power version, say, in the sense that if I apply lk, so if you want, you can say it L to the power k, to a random variable, the random variable will get lagged k periods. So L power k applied to yt gives me yt minus k. So it's tantamount of saying in words that you want to lag something by k periods. Okay. Now, this analogy between taking powers of variables and applying the leg operator k times will be very useful, because that is when the transition between logical operators, logical operations, and mathematical operations will happen. So essentially, I'm saying that there will be a situation in which we want to apply legs. This will be applied through the leg operator, and this will generate some object which we will interpret as an equation and solve it, finding the roots. And that's magic, because finding the roots of something which is not an algebraic expression will be revealing of the properties of the time series process. But I will explain myself better in a moment. Okay, the other operator is the difference operator. This one is more famous. Everybody's using it. Even people in do not do quantitative work. I think they learn the expression, the delta of something, the change in something, right? Delta is equivalent to talk about change, the spread. So the delta operator is taking a variable, in our case a time series, and applying a change, so studying the change of the variable. So delta yt is equal to yt minus 1. Notice that it's a more complex operator, because when you apply delta to something, you are contemporaneously doing two things. A, you're applying a leg, like the leg operator, but also you are shifting from studying that variable to studying a difference of the variable. So it's a bit more complicated than the leg operator. Delta and L, they are related in the sense that essentially if you want to lag a variable, so if you want to do delta yt, that is equivalent to apply the leg operator as 1 minus L times yt. So it's not just LYT, because otherwise they would be identical operator, but it becomes 1 minus L times YT. So delta can be seen as a kind of algebraic transformation of the leg operator, if you want to see it in this way. Okay? Now, because the delta operator is not just the leg, it's not the same, but it's the leg and the difference, it's a bit tricky. And sadly, I've seen pieces of programs, so software programs, wrong because of this, because there is a misunderstanding for what the delta operator is, and if you apply it in the wrong way, then it does not give the results that you want. Okay, so we have to be a bit careful when we use it, not really in econometrics too, in programming, if you happen to become a programmer. But you know, it's one of the mistakes that you learn immediately and you avoid. All right, so what is the point? Suppose that I want to apply delta squared to yt. So I want to difference a time series twice. Many people think that the differencing a time series twice is equivalent to what I will show you now in red. Red for mistake. Red for bad. In red, I said no. Red, okay. In red. Many people think that differencing a time series twice is this. So it's equivalent to studying yt minus 2. So I don't study just what happens to the time series when there is a period passing, but 2 periods passing. Okay, that's sensible. Unfortunately, if you apply delta squared to yt, that's not what you get. What you get instead, let me change color, blue. Blue is for good. What you get instead is what you see here. So delta squared applied to yt gives this. And this expression has nothing to do with the expression in red. Actually, in the red, yt minus 2 carries a negative sign in front of it. But in the blue expression, which is the right expression, yt minus 2 carries a positive sign in front of it. So you really do something different and you get different numbers. Now, if you follow the algebra in the slide, however, the nature of delta squared yt is compelling, in the sense that delta squared yt is delta applied over delta. But delta yt is yt minus 1. If I delta two variables, I get the difference of the variables. So I get delta yt minus delta yt minus 1. Delta yt is again yt minus 1, but delta yt minus 1 is yt minus 1 minus yt minus 2. But there is a negative sign in front of it. And so if you take care of the negative sign and you rearrange, you get the expression in blue, which is not the expression in red. Okay, so careful when you use it, because it does not have the intuitive meaning we want it to have. Okay. As I told you, delta has a clear relationship with L. 1 minus L is equal to delta. So if I want to difference a time series k times, I can write that as 1 minus L power k applied to yt. So to use one or the other is the same. Now, they're both used. Now, in what you will see in the next slide, there will be a lot of leg operator going on, okay? But in the future, it's a following topic. So it will be in 2 or 3 weeks from now. There will be also delta operator used a lot. Okay, what's the point of introducing these operators, especially the leg operator? Now, if you see the time series process, let me go back 1 second. In particular, if you see this way of writing, 1 second. This way of writing the time series process, you can recognize that you can do the following thing. You take all the values which involve legs of y, and you move them from the right to the left. So basically, it means that you're subtracting these guys, these terms, from both the left and the right. So the left becomes yt minus phi1 yt minus 1, and you lose it on the right, minus phi2 yt minus 2, and you lose it to the right, blah, 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 minus phi p yt minus p. So essentially, on the right-hand side of the equal, you isolate just constant phi0 plus epsilon t, plus the shock that moves the time series. Okay, so you can always do that. So you're just shifting things from the left to the right and vice versa of the equal sign. So, I mean, no problem with that. Once you do that, however, if you want to use the leg operator, you recognize that your time series process, your ARP, can be written in this way that you see in the square box in the slide. So it becomes an expression that involves powers of the Leg operator, so 1 minus phi 1L minus phi 2L squared minus dot 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 phi PL to the pth power times YT, okay, equal to the constant plus the epsilon t. So that's a white noise component that you got on the right-hand side, IID component even stronger, okay? Now, it turns out that the behavior, the statistical behavior of a time series process of the autoregressive p-type depends entirely, so it's entirely characterized by the properties of the pth order polynomial that you get in the parentheses. So by 1 minus phi 1L minus phi 2L squared minus dot 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 phi PLP. So by studying the properties of this polynomial operator, you can learn the entire behavior, so the entire characterization of the process. And what does it mean to study the properties? And here is the magic happening. So this expression that you see in parentheses is about taking legs. And taking legs is a very, is a very clear logical operation. Instead of considering YT, I want to consider YT minus 1. Instead of considering YT, I want to consider YT minus 2. So it's like moving in time, if you want. So getting random variables which represent the expressions, the realizations of a phenomenon before today. That's a logical operation. When people study history, that's what they are systematically doing. And there is no math in this choice. But it turns out, and there are proofs of that, so that's what mathematical statistics is about. So we're talking about the mathematical statistics of 100 years ago, a bit more, something like that. It turns out that if you interpret the quantity that you see in parentheses, so let me emphasize that, this guy here, just this guy. If you interpret that as a mathematical expression, you equate that to 0, and you find the roots of what looks like a polynomial, you are discovering entirely the behavior, the properties of the time series process that you have in front of your eyes. So the suggestion is written in the slide, is that you replace L, which is a logical operator, with lambda, and you interpret lambda as a real variable, just a variable, okay? And therefore, you make of the expression inside the square, I will redo it, so this guy here, you make of that a polynomial equation, so you equate that to 0 and you study that. It's called a polynomial equation. It's also called the characteristic equation. And to study that means what? Well, if I give you a polynomial in mathematics, the thing that you normally do with that is to find the zeros, the roots. What are the roots? The values of the variable L, lambda, let's call it lambda for convenience, which solve, so they verify the equation. And in general, remember that if I give you a pth order polynomial, it will have p roots. Not all the roots are guaranteed to be real roots. Some of them, they may be complex numbers. But in general, if the order of the polynomial is p, there will be p different roots, which you can find solving it. So there are methods to solve equations, as you will remember from your mathematics. Now, once you do that, you have a machine doing that for you, don't worry. So there are tricks to do that, and anyway, will be very fast. By inspecting such roots, so the values which represent a solution to the characteristic polynomial, also called characteristic equation, you will know everything there is to be known about your process. What do you want to know about your process, your ARP process? First, whether it is linear or not. Second, whether it is stationary or not. If it is linear, then weak stationarity will be the same as strong stationarity. If it's not, then there can be a difference. So you may be interested in studying both weak stationarity and strong stationarity. So all these properties, they just come from inspecting, studying the roots of the characteristic equation. And what are you supposed to study? So once you have a root, the root is a number. So what do you see in a number? So there are two features you care for, whether the root is real or not. And you're asking, so, okay, there are real numbers, right? I know, but what is not a real number? Well, as you know, there are complex numbers. Complex numbers derive from generalizations of real numbers, and they give a meaning to the notion of taking the square root of -1, so taking the square root of a negative number. Okay, that's one way to think about it. Now, we don't care for working with complex numbers, but we want to recognize when the roots of the characteristic equation are complex. because they will define a special type of behavior by the time series. And we already encountered that. And I said a few things that if you listen them again, they were mysterious on purpose, but now it's time to actually reopen them. Remember, the ACF of a weakly stationary process can die in a convex smooth fashion, or it can die off to zero in a sinusoidal fashion. So basically in an oscillatory fashion. And I said, well, this will depend from some properties of the time series process that it will be possible to find, to detect. What are the properties? What are we talking about? Answer, when the roots of the characteristic equation of a AR process are complex, there will be oscillatory patterns in the way the ACF behaves. More to come in the future, so with examples. Second, if I give you roots, complex or real, you can study their absolute value, let's call it this way, okay? And you will see that it makes a big difference whether the roots are in absolute value less or above 1. But I think it's 11:52 and I'm supposed to stop. Okay, guys, I will stick around for another couple of minutes. I have another class coming, but I will stick around for a couple of minutes in case you have questions to ask. And otherwise, I will see you tomorrow. I will decide in the next few hours whether the class tomorrow can be physical or not. But if I don't receive any other instructions, it's very weird that some of us are actually locked in and have to be tested, but at the same time, the others that we have met until a few days ago meet in the classroom. So I feel that there is an inconsistency there. And so we may go remote again, but I will ask my department what they think about it. Okay, so but I will let you know in the afternoon at most. Ciao, guys.